Yeah, actually, I might have to be even a little more careful here, right? Because what if P and Q are on opposite sides of this picture? Then they're within 2 delta x of each other, and I want them to be within delta x of each other. So, so I need to modify something here. Oh, yeah, that's right. You only care that they're close to x. Thank you. Awesome. Great. Good. Okay. Think too hard about things and then it becomes more confusing. Okay. Great. So here's the question then. Is this true? And the answer is yes. And this is actually a famous lemma in its own right, and it's such an important fact that it has its own name. It is what's called the Lebesgue covering lemma. That's an excuse to prove something that's not covered in your book, but is used very, very often and in many contexts. So the Lebesgue covering lemma says the following. It says if you have, let's say, an open cover, U sub alpha is an open cover of a compact metric space X. Notice the compactness of the space X. Then, in fact, there exists a number delta bigger than 0, such that for all x in X, the ball around X of size delta is contained in some element of the cover. Is contained in some U sub alpha. That's the statement. And this delta has a special name. It's called the Lebesgue number of the cover. And this Lebesgue number will be, it will exist and be bigger than 0 if this space is compact. So here's the picture you should have in your head. We have some space. Let's call it X, and it's covered by a bunch of open sets, like so. And the Lebesgue number is basically a number, delta, such that you give me a little pancake of size delta, or radius delta. And if I throw that pancake anywhere in this picture, I claim it'll land completely within one of the sets. If there is such a number, it's called the Lebesgue number. And the claim is if the space is compact, this will be true. And can you see in this picture how small delta might have to be? Yeah, would you agree if I have a pancake of about this size, no matter where I put it, it'll lie completely within one element of the cover? Yeah? Now, this would not be necessarily true if the space were not compact, right? Imagine the following space. The open interval. Well, we can certainly cover the open interval like so. Let's just take a bunch of intervals that are basically narrower and narrower and narrower and narrower. These are all open. Imagine these all be open sets. Throw a pancake down of any size and you're in trouble as you get closer and closer to the right. Okay? Well, it's not true if the space is not compact. Okay. And that's what we're saying here. If there's a pancake you can throw down so that it lands completely in one of those delta x balls, that's the delta that I'm interested in, then we're in good shape because we'll be able to complete the proof as desired. Okay? So let's see why this Lebesgue number exists. Okay, well, how might we start off this proof? Give me some ideas here. Space is compact. I have an open cover. Let's do something. Okay, yeah, how about take a finite subcover? Okay, well, how's that going to help me? Since X is compact, there exists a finite subcover. Let's call it U sub alpha sub I. And let's say I goes from 1 to n. Okay? So then what? Now I can remove all but finitely many of these balls. That's nice. Jenny? Okay. And what's your idea here? So you take an intersection of them and? A minimum ball, a ball of? Okay, so like as long as it's non-zero, as long as the intersection's not empty. Okay. And so why is that going to be a good pancake? It's actually it's a natural idea. You're sort of saying take something like this. And now which ball? Maybe this one? Okay. I'm a little worried about the same ball if I just move it over a little bit. Just a little worried. Although the intuition is a good one, but one has to be really careful because maybe it's not pairwise because you might have a really small. Should I look at all possible non-zero, non-empty? Okay, it's hard to do this. Although I think if you're careful, you can create an argument like that. But I'm going to use a very similar idea here. So, how about the following? Would you agree that if these sets are open, then their complements are closed? Yes? So it makes sense if I have some point here to talk about the distance between X and, let's call this set. If this set is a particular set U sub alpha, then everything outside is U sub alpha complement. Yes? That's closed. Would you agree it makes sense to define a distance between X and the closed complement? Let's make a definition, and I'll convince you that this actually makes sense. Would you agree if a set K is closed, you can't stop me from defining a notion of distance between them? How about this? The distance between X and K is, how about the infimum of all distances X and Y, where Y is in what? K. Okay. Now, what can I say about this distance notion?